Okay, let's get started. This is my last lecture for the term. Then I turn it over to you guys. So I want to give you at least a little. Normally I spend a couple lectures on this, but somehow with the project presentations and also just the schedule the way it's played out, I get only one lecture on learning. But we'll do a little bit of learning and try to give you a sense for at least my view of where it fits into the concepts we've developed so far in the course. And I also get to sort of summarize what happened, right? Just to make sure that you guys remember some of this or have it in context, and I get to talk about the bigger picture, right? So let me start with a little bit with that, and I'll put the learning in context with that. Okay, so we've covered a lot of computational methods in the class, right, from DP to local linear feedback. This is in general for nonlinear control and planning, right? So DP, LQR, sums of squares for the Lyapunov methods, like with sums of squares, trajectory optimization, trajectory feedback. We did randomized motion planning a little bit. We talked a bit about stochastic and robust control as an addition to that. Right, and these tools that we developed, basically, they work pretty well. Well, they work to varying degrees. You know, DP will work extremely well for all sorts of problem formulations for very small problems. LQR works very well if it's linear and works okay if it's nonlinear, and so on and so forth. They all have their limitations. They all have their things that they do extremely well. You get to get the intimate details of that on your projects, right? These have been demonstrated in general, you know, on real robots. We've shown their extensions in almost every case to hybrid systems. I mean, they're pretty general tools. You know, for low-dimensional systems, we can basically solve to our heart's content feedback controllers that we could say every initial condition that can get to the goal will get to the goal, given this, and we can give you a certificate saying, you know, giving you some confidence that that's true. But I would say everything we've talked about so far, every single one of these has at least a couple flaws, right? Maybe two big flaws, right? And I want to make sure that I express those and I don't leave you, you know, thinking it. So at least two big flaws. Or assumptions, let's say. Right, so first of all, we assumed we had a good model, right? Or we did robustness a little bit, but somehow we've developed a set of tools which will work best if the model is good, right? If we can come up with an ODE model of our complicated system that we can reason about, right? And you know, for some of the complicated systems, we'd like to write down a PDE, but we really have our best tools are for ordinary differential equations, right? We've basically been assuming that, maybe, you know, plus some uncertainty, but we've really been pretty model dependent so far. And the other one is we've assumed every one of these methods we've talked about so far is a full state feedback method. Right? We've assumed somehow that we've been able to estimate the state of the system with some state estimation or something like this. Right? So this one means we're sort of very dependent on system identification. And this one means we're very dependent on state estimation. And these are things that keep me up at night, right? It's real. It's true. I mean, we really, we can, in some cases, give certificates saying that we have some robustness to these things, but fundamentally we've given a model-based approach so far, right? So I would go as far as to say that, for the pendulum, we can throw the book at the pendulum. Every one of these tools, I showed you an example on the pendulum, right? And when it's all said and done, I think our best computational tools come up with controllers that are inferior to the energy shaping control, right? In what way are they inferior? I can give you a better proof in some sense of the trajectory optimization plus feedback plus everything, but somehow if you have a pendulum sitting in front of you and you've just quickly estimated the parameters of the system, you don't know the friction exactly, you don't know, you've got a quick and dirty state estimator that you put on the system and you just want the thing to swing up and balance at the top, you're going to have more luck immediately with an energy shaping pump-up controller than something that we've designed so far. And I mean, that's where we're at right now. I mean, I think that that we can use these tools. I think the long road is to use these tools and to, for instance, include the state estimation in the model, do verification and control design through the state estimation, to ask in the right way for robustness to the right real quantities. And I think a solution that should emerge through very nice application of these tools would be something like, if the best controller is energy shaping, then that should actually pop out of these tools. But I haven't seen that happen yet. I feel like we're getting close, but we're not quite there yet, right? If that does happen, then I think these tools will let you do it for many more complicated systems than the pendulum, right? It just happens that in the very, very simple systems, we have handwritten controllers that we know to be good. But if you wanted to do more complicated systems, these tools will scale, and somehow if we can write down the right questions for those complicated systems, that's where I'm putting my money, is figuring out the right way to encode robustness and ask for the right thing. But we're not quite there yet. I mean, I think we're on the long road to the right place, but we're still losing to energy shaping. Okay, so I mean, I think that's important to say, right? Let's think a little bit about what it would take to finish that road, maybe a little bit, right? So the problem of doing control design of an estimator plus a controller simultaneously, that's a well-known problem. It's called the output feedback controller. So say simultaneously. Or more generally, a feedback controller that takes the sensors as input. This is the output feedback problem. Right, so just to be very clear, what we're doing right now, we have some plant which has some sensor readings coming out. It has some internal state, X, but we don't actually get to measure X directly. We get to measure some noisy sensors potentially. So we've sort of implicitly assumed here, well, that in simulation or in modeling, we can just get access to the state directly. But in general, we have some state estimation going here, which is going to give me an estimate of the state, which I throw into the feedback controller. Which gives me my U, right? That's the sort of loop we've been assuming. We've mostly not focused on this because there are other courses that focus a lot on that. But that's sort of been implied, is that if you go to implement it, you're going to have to somehow get your state, estimate your state from the noisy sensor readings, right? The output feedback problem is, in the most general sense, designing a controller that takes and goes from Y to U. And of the solutions, of the techniques we have for output feedback design, there are, of course, any of the tools that we use in class could in some way maybe be put to task to try to do output feedback. But it's sort of surprising how few results we have, rigorous results we have about designing controllers of this form. Okay, even for linear systems, this is considered an open problem. Let me be clear, okay? So you could think of the one result we have in the output feedback world is the shining result sort of is LQG, is the linear quadratic Gaussian, which says we do an EKF, or just a Kalman filter here. You do a Kalman filter to get X hat, and then you do LQR to get U. This is optimal output feedback for the special case where you've constrained the number of states in my controller to be the same as the number of states in my plant. But you have to think of this, so the Kalman filter has its own internal state. My point is just that this is a subset of the output feedback control problem. It's one example that where we know how to solve it for a linear quadratic Gaussian system, but actually even linear systems, this is hard. If you asked, for instance, if you asked me to design the best controller, which is just a simple linear controller of the sensors, a linear feedback on the sensors. This is the static output feedback. I don't know how to do that for a linear system here. It's sort of shocking how few results we have here. LQG is the one example. And it happens that for linear Gaussian systems, if you're willing to have exactly the same number of states in my dynamic controller as my plant, then I have a Kalman filter plus LQR as a solution. And so that has justified us, in some sense, thinking about only feedback for a while. But really, there's hard problems that remain, okay? Now, I want to talk today about methods that could potentially design output feedback controllers for us, okay? But let me first convince you that even, why we should care, right? Okay, so we know that this is only optimal in the linear Gaussian sense, and we could potentially do better. There's other reasons to care too, right? So one of the ones that's come up recently for us, especially for Ani and me, we've been talking to biologists about how birds fly through forests and things like this, right? And similarly, of people studying simpler insects flying through obstacle fields and things like this, okay? Experimentally, if you look at how these guys fly through obstacles, a lot of times their control decisions can be modeled very well with very simple feedback laws. I think the biologist's view of what's happening when a fly is navigating a forest is they see some things over here looming, they see optic flow over here, so they go this way. Or they see something over here, so they go this way. And it's a very simple, sensor-driven, sort of reactive control strategy that can really, can be written down in very simple static output feedback form and can describe nicely the performance of a lot of these animals, which, frankly, is still better than most of our robots, right? So maybe there's something to it, okay? And I just think that, in general, this path here of going through the state estimate and through full state feedback is not always the right path. There's just places where if I am a bird flying through a forest, right, I don't really need to know my global position in the world. I don't really need to know what's going on over there. I don't need global state information to make my decisions, and I shouldn't. And my controllers are more frail because of it. So I think ultimately, when we get good at robustness, I think controllers that are more like this will pop out. Now, of course, an output feedback controller that is allowed to have state is a superset of the static output feedback. So these are always going to be better than static output, or at least as good as static output feedback. But somehow I just feel like we're putting artificial requirements to estimate state, have a dynamic model into our systems that don't need to be there. Okay, so let me give you. The other reason to do it is that there's some times where we just don't have a good model. Period. Right? There's some systems where I can't describe in a useful way. Starting from physics, starting from the Lagrangian equations of motion, is sort of not the best way to get to a controller for my problem. And that's what I want to talk about today with some of the learning controls. The learning control techniques we're doing today are going to be a different approach to try to get this sort of directly, not by a model-based approach, but directly searching over the set of control policies that would map me from sensors to actions. Okay? And it's a fundamentally different approach. I personally think that when you have a rigid body system that has n links, even if n is fairly large, then there's so much structure in that you should really be using model-based tools, and that's why we spent almost all the term on it. But there are some great problems there where it's not the right way to start. And my favorite example of that is in fluid dynamics. Okay. So let me give you a model system, my favorite model system from fluid dynamics to motivate sort of the discussion, okay? And that is the heaving foil by Jun Zhang at NYU. Okay, so we are interested in flapping flight. We've built robotic birds upstairs and everything like this, and robotic birds are just complicated. We try to build the simplest possible things, but we still, to make the thing fly, we needed aeroelasticity. We got these nylon wings that are flapping and bending and morphing and doing complicated things in the airflow, and it's been really hard for us to get our head around what's the core simple model for flapping flight. And then I met Jun, and Jun has this just beautiful, simple model of flapping flight. Okay, it's a heaving foil, and this is really what it is. It's a symmetric flat plate. Okay, it's driven actively up and down, right? It's driven vertically. He actually has a prescribed position trajectory. That's not fundamental, though. And then it's free to translate horizontally. Okay? Now, you'll see why it's so compelling if I show you the video, okay? So this is Jun's lab at NYU. Jun's lab, by the way, is just so amazing because he's got more pictures on the cover of fluid dynamics journals than anybody else I know. I guess I don't know all the fluid dynamicists. But you go into his lab and you expect to see this sort of this beautiful workshop with high-end equipment and everything like that. He's got whatever he bought in Chinatown. He's at NYU, and he's got like his cell phone cameras. He says this MacGyver-esque approach to science, and it's so compelling and it's so awesome. He's got a water tunnel. It's something he built himself out of little mylar sheets, and it's just awesome. So the video you see here, it is literally a basin he bought in Chinatown. Okay, and it's a couple of ball bearings and a piece of steel rod. Okay, this is his experiment. He was actually just driving it through sinusoidal trajectories vertically, and look what happens when he takes videos. Okay, so this is so he's rotating. His approximation for going straight forever is to rotate around in a circle, and just look at how beautiful that is, right? So Can you see what's happening? The plate's going up and down. It's coming around here. And can you see the vortices being shed off the back there? It's just so clean and so good. Okay? So the way you do these kind of experiments is somehow you seed the fluid with particles, you hit it with a laser sheet so that you can just illuminate a column of the particles. You take use some high-end laser, high-end camera, whatever. So June just stirred it up and got a bunch of bubbles in the water, and he's just, it's just amazing what he does with this. But the story of this flat plate turns out to capture, in a lot of ways, the fundamental dynamics of flapping flight. Okay, let me see if I can cartoon it for you and channel June for a second here. Okay, so what happens if you take a symmetric flat plate and you just start driving it vertically? Okay. So the first thing that happens is that if you just pull down, then what you get is at the onset, you actually get a symmetric vortex wake. Okay? If you were to pull for a long time, if you guys know fluid dynamics, right? If you pull for a long time, this will actually start shedding a periodic wake. There's an instability there, but if you pull for a long time, you'll get a vortex street, a von Karman kind of wake. But instantaneously, it's actually a symmetric wake, okay? And so the water's spinning around like this. And the dynamics of the plate in the horizontal plane are governed by, there's water shooting this way, so it's sort of pushing, by just friction with the water, it's pushing it this way and it's pushing it this way. Okay, so there's these forces, balancing forces on the plate from the spinning fluid, okay? And they're symmetric and opposing, until something happens, right? Something's a little bit imperfect, something's a little asymmetric, because there's going to be some imperfections. This is going to be an unstable fixed point, okay? It's just like our pendulum balancing at the top. This is an unstable fixed point because as soon as it starts moving to the side, if it has a little bit of horizontal velocity, okay, then now the vortex wake is going to look like this, right? And the forces here are going to affect the plate more than the forces over here, okay? And you'll end up getting this thing moving forward until these horizontal forces that are sort of propulsive forces get balanced by drag coming back, and this thing will end up moving forward into a steady, symmetric, flapping flight, okay? And if you start it up experimentally, you start driving it vertically, there's a 50-50 chance it'll go left or right? Whichever way it goes, it'll speed up and it'll go to its comfortable speed, which is a simple function of the pumping, flapping frequency, and it'll be very stable there. And then if you were to stop it and redirect it the other way, it's just bistable. Two very stable fixed points, an unstable fixed point in the center. Okay? It's one of the simplest models of flapping flight. I haven't found a better one. I think it captures a lot of the challenges of sort of doing control with fluid dynamics, right? Why is it hard? If you think about it, we know the governing equations. We do have a model. It's Navier-Stokes, right? It's just sort of not a useful model, or it's not useful to me as a control designer. It's too complex. It's a big PD that I have to simulate. In fact, there's a great group that's worked on this, right? So they have good CFD codes that model this horizontal flapping flight, and it takes, let's say, the CFD. Last time I talked to June, the computational fluid dynamics, the direct numeric simulation of this, it takes a little more than 1 day to simulate 30 seconds. Right, and you know how many iterations your trajectory optimization took, right? So, just take that and multiply it by a day, and you see how long it'll take for your optimization to converge, right? There's people that do that, but it's tough. Now, I haven't talked to June about this particular thing in a little while, so maybe that's half a day now, but still, it's extremely slow. There's a lot of good work in fluid dynamics about coming up with lumped parameter models of ODE approximations of the PDEs in the flow. And those were starting to come online for this heating plate, but they're not as nearly as predictive as the full model or the real system. Okay? You know, but in general, there's still feels like a lack of tools for generically coming up with ODE approximations for these types of systems. Those of you that are in fluids, I mean, so Galerkin methods and things are the rage, but they're actually exactly the case where the Galerkin methods are known to fail in the sort of these time varying transient dynamics at the beginning. That's the worst case for the sort of Galerkin projection type approximations. Okay, worse than this, I think, is that not only is the simulation sort of slow, but it's also extremely sensitive to the geometric models of the system, right? So I learned from my fluid dynamics friends, you know, basically, I remember we had one airplane that we were doing perching with that had just a foam wing, and then we had a second one which had a stiffening bar just to make sure that the wings didn't flex too much, and we had engineered this to be, you know, basically perfect. You could run your fingers over it, not really feel any difference, whatever. And I remember my aerodynamicist friends looked at it and said, "That's a completely different airfoil. That is, you know, you could trip the boundary layer and just have a different system there. Don't even pretend that that system is the same as that system. Those are completely different, right?" So that made me extremely paranoid about fluid. I mean, about sort of the sensitivity of the models that we have in fluid dynamics. Obviously, the airplane's going to, in net, sort of do pretty similar things, but the details are going to be could be pretty different. Okay, so there's also a lot of sensitivity to geometry, to boundary conditions. Okay, so this is sort of my favorite example of something that seems like such a simple, easy problem. I mean, you could ask, like, okay, well, I haven't named a problem, but maybe if I wanted to do, you know, this is the equivalent of what we've been doing for walking. Let's say I want to find a periodic solution of my system, which, for instance, maximizes propulsive efficiency. Right? Let's say if I'm allowed to drive it however I want, how should I drive this thing in a periodic motion to make it as efficient as possible in forward motion, right? I could take the class's worth, our whole class worth of computational tools and try to throw it at that, and it would be very, very hard, right? So at some point, I think a different approach is warranted, and the approach that I'm going to advocate today is sort of a learning control approach, right? And this is a canonical system where I still really believe in the model-free, if you will, approaches to control. Now that's a model-free means different things to different people. People hate that name. I don't particularly like it, but I'm using it to contrast it from the Lagrangian type models that we've used to start heavily in the class. Okay, so here's an idea. Instead of doing some, you know, exploiting the gradients of a trajectory optimization or formulating the problem as polynomials and calling sums of squares, let's just do generic. We're still going to do optimization, of course, but let's just do generic black box optimization. Okay, so let me say that I have a cost function. J, it could be a function of my initial conditions, x, and it's some, you know, integral. It's still the same framework that we've been doing the whole time, okay? But let's say I don't actually get to evaluate this myself, but what I get instead is just the ability to evaluate. If I have a function, a black box function, that if I give it x0, it gives me the value of j back, right? question is, can I still do some meaningful, efficient optimization given that world? And of course, the answer is going to be it's not as good as what we could do if we are allowed to dig inside, but we can still do something, right? So, for instance, if I want to do gradient descent, then, but I don't have access to the derivatives directly. There's a number of things I could still try to do, right? I could do finite differences to try to estimate, right? I could, one example is finite differences. So I could say that in every direction, right, I'll sort of compute the sensitivity to each parameter independently by perturbing it in each direction, try to evaluate it twice, once with the perturbation, once without. Where let's say this is a perturbation and just right, I could just sample, I could just change each parameter one at a time, see what happens, change each parameter once at a time, and estimate the gradient. And then I could do my gradient descent optimization. You could try even computing a higher order a Hessian, let's say, and doing second order optimization. All these things are potentially possible. Okay, but what if we make the problem a little bit harder, which is, let's say that every evaluation of J takes me, I don't know, a day, if it's a simulation, a CFD code. Or at least it's, it's expensive in the sense I have to pick my robot up and let it run for a little bit and fall down, maybe break, and have to rewire it and then put it back up and try again, right? What if each of these J's is expensive? This becomes one of the key questions in the learning control literature. It's actually, there's of course all the discussions that we've had before about have we written down a convex optimization so that we know the gradient descent would do the right thing. All those questions are still valid, still relevant, but they're not the focus because typically in black box optimization, I don't hope for having necessarily found convexity. I'm happy to just do gradient descent and at least find a local minima for now. And if I can do that efficiently, then there's another problem to solve. But it's hard enough to just, on my real robot, optimize any old objective to a local minima. So let's focus on that first. And one of the names of the games that we can play here is, how can I minimize the number of evaluations of that function to try to, climb down a gradient and find my local minima. And the answers I can give are only partially, they're only sort of steps in that direction, but there's a nice big body of work out there on people that think about this and have done, really nice things in this space. Okay, so one of the first ideas is that that if we every time we have an estimated parameter alpha. That's my control parameters, right? I've got some controller parameterized by alpha. I try to put my robot in the initial conditions. I evaluate it at alpha. I change alpha a little bit. I evaluate it, and I change it in every direction. If I'm doing that in every direction from every alpha, I'm sort of wasting time, right? I shouldn't have to evaluate every possible direction and every possible step. So let's think about doing something a little bit faster or a little bit sloppier potentially, which would be a version of stochastic gradient descent, okay? So if I have some function I'm trying to evaluate, j of alpha, and it's some complex high-dimensional thing, right? So gradient descent would be, in some sense, the steepest descent towards a minima. But it's expensive to compute the gradients exactly. So one of the games we'll try to play is, can I get down this to the bottom with less evaluations by doing stochastic gradient descent, okay? So really the key observation is that as long as I'm going downhill on every step, I don't have to estimate the gradient perfectly, but as long as I'm always going downhill, then I'll eventually get to the bottom of this basin. And if I can quickly estimate something that's going to get me downhill, even if it's not perfect, then maybe I can actually get to the basin faster than if I was doing perfect gradient estimates at great cost on every step, okay? It's really a Lyapunov argument, right, for the optimization space. Okay, so here's a slightly different algorithm for you, which I think is the first way to think about a learning control black box optimization. By the way, so this set of algorithms has a bunch of different names. So in the machine learning world, this is a version of policy gradient reinforcement learning. In control, it's often called extremum-seeking control. And I would say in general, the extremum-seeking control people don't read the policy gradient reinforcement learning papers, and the reinforcement learning people don't really read the extremum-seeking control papers. And they don't like each other, they don't cite each other, they do the same things, mostly. I'm guilty of it, for sure. There's also iterative learning control is another very close branch. But there's lots of good work that's been done out there by 2 independent communities. Okay, so here's the sort of simplest policy gradient reinforcement learning or extremum-seeking control algorithm. Okay, let's just assume, we'll call it weight perturbation. We'll assume that J is smooth, or at least differentiable once. Okay? If I can assume that J is smooth, then I can say, if I were to take my J at with some control parameters alpha and evaluate it at a neighboring point, let's say I'm going to change my parameter vector alpha by some, let's say, small random vector. So I'll just change my controller a little bit. Then I'd like to be able to say that that's going to be approximately that for small beta, I can approximate that with a first order Taylor expansion. That's reasonable if this thing is smooth. Okay, so the simplest update I could imagine doing, which is short of estimating the gradient perfectly, but will still get me to the goal, is if I take my parameter vector alpha and I evaluate the system twice. I'll evaluate it at alpha, I'll evaluate it at alpha plus beta, I'll take the difference and I'll try to go downhill. Okay? So basically, you know, if I changed my parameter vector and it got better, I'll go in that direction. If I change my parameter vector and it got worse, I'll go the opposite direction, right? And I'll take a step in that direction by how much I got better, right? So that looks something like this. I'll have some learning rate, some rate I'm going to go downhill, same as my gradient descent. And if I insert this approximation, this Taylor expansion in here, I can rewrite this as I put my j alpha plus beta as j alpha, just cancels that out. All I'm left with is this term, and then just taking a transpose because that's a scalar. Anyways, this is my result. I can say that my update to my parameter vector alpha, if I just do that, if I just change my parameters in a random vector and then take the difference in the cost I got and multiply it by that random vector, and I'll go in that direction, right? Then what can I say? I get this rule coming out, which is in the direction, this thing's positive, so this thing is always within 90 degrees of the gradient. So I will always go downhill, check. Even better, if beta is some random variable, and I choose it independently, then the expected value, right, of E alpha is just eta times the expected value of beta, beta transpose. Let me write that on someplace I have more space. The average direction I'm going to go down, I'm always going to go down within 90 degrees of the gradient, but the average direction I'm going to go down this thing is like my covariance, for instance. Covariance matrix in general. So I'm always within 90 degrees of the gradient. And on average, I'm in the direction of the true gradient. Okay? So here's a proposition. Don't try to do finite differences every time. Just pick a random small change of my parameters on every step. Go in the direction or opposite the direction if it was bad, or in that direction if it was good. And what I'm saying is that with a trivial update, on average, since I'm just picking at random, even in high dimensions, on average, I will go down the true gradient. And I'm always going to be within 90 degrees of the gradient, so I can make a Lyapunov-like argument saying I will eventually get to the minimum. The cool thing is if you do some basic counting arguments, now we don't know we can't estimate the number of steps it's going to take to get to a minimum. That's hard. For a quadratic bowl, maybe I could, but in general, I don't know that. But what I can do is I can give you a variance argument on, how many updates it takes to get a reasonable low variance estimate of the true gradient. And this method, as naive as it sounds, outperforms finite differences. It takes less samples to go downhill on average by that surrogate. I'm going to get a better estimate of my gradient in less samples if I choose randomly on each time and go downhill than if I were to stop and take every possible sample every time. That's kind of cool. Yeah?
So is every iteration completely independent, or can
Yes.
you somehow use information?
So for now, going downhill argument so far depends on it being independent, and then we're going to do even better if we reuse past information, but we have to be careful not to introduce correlation into that process. Yeah? Great question. Right, so the first reason to do what you say is that there's one fundamental problem with this. It turns out we can do even better. This one takes 2 updates for every 2 evaluations of the function for every update, right? And so you'd like to say, oh, I could reuse my past experience and get rid of this one, for instance, right? That would be good, and especially if that's going to be especially important if these become noisy variables. If I don't get to measure exactly the same cost every time I run my robot, let's say the robot's a little random, or I can't put it back in exactly the same initial conditions, and so every time I get a slightly noisy evaluation, then it's going to be important to have more robust versions of this, which only require a single update. And it turns out you can do that. If you can replace this with an estimate from history, you can be bad. You can break the downhill convergence. If you're careful, though, you can do a good job of this and increase my signal-to-noise ratio of my estimate, and be more robust to sort of noisy evaluations. Okay. Now, I actually normally spend a lot of time going into exactly what that is, how you do that. The short story is there's a long answer. Okay. The short story is that one of the best things you can do here is to actually estimate the cost to go. You can learn a value function, for instance. From your noisy data, try to approximate my cost to go over my state space, and insert a value estimate here, and stick that in. But the story I can tell you simply here is that even if I just pick a bad baseline here, if I were to do something like this, this is just some baseline. Okay, all that I require is that little b is uncorrelated from beta. Then I still go downhill on average. Then I can still say that so if I were to just stick in a random number here, as long as it's uncorrelated from beta, then I can still show, with the same argument I did before, I can still show you that on average I'm going to go downhill, but I lose my guarantee, my Lyapunov-like guarantee. Write Gaussian and guarantee so often that I always find myself writing them backwards. Okay? But there's a cool set of algorithms that emerge from doing this, right? Okay, now all of the, so you can do variance analysis and signal-to-noise ratio analysis of these types of algorithms. One of the most important things I can tell you is that the signal-to-noise ratio, which is a surrogate for how fast I'm going to converge, it depends on sort of, let's say, let me write it. So it's sort of the direction of my update that is in line with the true gradient versus, that's the signal, and versus the magnitude of my update, which is orthogonal to the true gradient, that's the noise. If I analyze the signal-to-noise properties of these types of algorithms, one of the things you'll find is that the signal-to-noise ratio, and therefore roughly the convergence rate, depends on the number of parameters, alpha, but it does not depend in a direct way on the shape of J. Okay, so it's sort of one of these bizarre things about black box optimization. I guess I'm saying that if you're so naive to ignore the dynamics, then what you get for it is that you're unaffected by the complexity of the dynamics. Okay, so if I wanted to optimize 10 parameters on a simple pendulum, right, then I could do that, and I can give you a signal-to-noise ratio argument saying it'll take about this long to converge to an optima. If I take that same 10 parameters and try to optimize a Navier-Stokes simulation, or or a robotic bird or something with 10 parameters, it's going to take me the same amount of time to converge, right? That's somewhere in between this magical properties of these algorithms and just the naivety of the algorithms, right? Like it's sort of it's because I haven't looked at the dynamics that I'm unaffected by them. But it's kind of cool that I mean, imagine yourself, what you should think of is that, imagine you've got a little robot sitting in front of you, and you've got a mixer with 10 sliders on it with your control parameters, right? And you're going to let the robot run, and you're going to sit there, and you're going to tweak the mixer until the robot runs well. If it could be a walking robot with hybrid dynamics and stick-slip friction and whatever like that, I'm still going to just knock my parameters around about the same way, right? It doesn't really matter. So these algorithms, I think, don't have a great story to tell on pendulum, where we can do better. But on a Navier-Stokes simulation, where we don't have a good model-based approach, these can be very powerful. Okay, so we were so excited with June's stuff that we went down and tried doing some policy gradient learning on the heaving foil. Given exactly the problem formulation I sketched before here, we said let's optimize the stroke profile of the heaving foil. We'll find a periodic solution of the system in the vertical trajectory, which maximizes propulsive efficiency in the horizontal direction. And no models whatsoever. Let's just run the experiment. 30 seconds experiment takes 30 seconds to evaluate, right? And you can actually be even a little bit more clever. You can do it sort of online. You don't have to stop in between if you get the baseline calculations right. You can just do it while the thing's running and back out updates. And this is what it looked like. We got fancy enough. The best video I have where you can see the whole setup was it had a wing on the back too, so that was an asymmetric foil. Okay, but the cool story was in 40 iterations of the algorithm, which was like a few minutes of experiments on the real robot, minutes, no more, like less than 5 minutes. We found a convincing optima, which was dramatically more efficient than anything that was predicted from CFD or the ODE models, right? And it wasn't an approximation, it was running on the real robot. You could measure the efficiency, right? And it was just by doing we parameterized the periodic solution with the spline parameterization, with knot points. We changed the value of the knot points, ran a trial. We're clever about the signal-to-noise ratio and tried to add noise in exactly the right way to continue to update our system effectively. And in a few minutes of experiment, you can optimize pretty complex things, right? And it would have taken just as long to optimize a pendulum with those many parameters, right? But now we're doing this hugely complicated fluid system. And lots of other people have done this too. So this one is our local Andy from Daniela's group upstairs. Many of you know. He did this on his robotic fish. Actually, this was the first version of this was his final project for the class. But then he went on to, it's on the cover of Soft Robotics and other things, right? So he did a great job optimizing the efficiency of his soft robotic fish. This is his cost over time, and he's got this robotic fish now that was hard to program, but swims pretty well now. And the cool thing about this is not the way it flaps its tail, but that is cool. But it's a cool fish for other reasons. Everything's internal. He's got a sort of an amazing mechanical design there. So I think there's hope for this. I think fluid dynamics is my favorite example of where these learning approaches can really, really pay off. There's lots and lots of very simple experiments in fluid dynamics that I think are hugely complex to write down, but extremely beautiful and simple. This is another one of my favorite experiments by June. So, and we've built it upstairs. You can do this yourself. It's very easy, actually. So this looks incredible. Anybody guess what that is? Anybody know what that is?
Trail behind the cylinder?
Say it again?
The trail behind the cylinder in flow?
There's definitely a cylinder there, but there's more going on.
It's an oscillating, doesn't it oscillate back and forth behind the cylinder? You have flow head towards it.
That's true. A cylinder wake would have something like this, but this is more than that. It's a very good guess. So this is actually a piece of thread on a soap bubble. Okay, so one of the simplest experimental fluid dynamics things you can do is you can take two pieces of string, put a tap at the top, put some dish detergent on it, pull them apart, and you have a falling soap film. It's literally a soap bubble. It's falling down on the water, a little waterfall. You don't breathe because you don't want to pop it. And then one of the cool things you can do is you can hit it with a monochromatic light, and just the refraction patterns from the monochromatic light show that, I mean, if you look at a soap bubble, you see all the patterns. That's the density of the soap bubble that you can see in the soap bubble. And it actually, as the falling soap film, it shows you the flow lines of the fluid, right? It's a beautiful visualization. So June did that, and then he put a little string on top of this falling soap film, okay? It's from here to here. And he observed something fantastic, right? So if it's certain length, you can change the length and you could get slightly different effects, but in some intermediate length, it's bistable. So first of all, there's a steady state solution with the thread just going down and the water going around it. But if you knock it a little bit, it has a stable periodic flapping solution. Okay? This is like a flag flapping in the wind, or maybe a passive fish sitting in a wake, but it's got a stable periodic solution. And the cool thing is the short string only has the stable downright solution, and as you get longer, it goes through, it only has the flapping solution. And the wake is just fantastic. So I would love to do feedback control for this. I so wanted to do feedback control for this. But we tried voice coil actuators and everything. It's just too fast. You can't process it fast enough. The dynamics on the soap film are just too fast. You actually need inertia to slow things down. But the dynamics are beautiful. Right? This is high speed slowed down. It throws these vortex wakes. And there's other things that are just these really simple, beautiful. People study falling paper, They tumble, it rolls, right? The dynamics are beautiful and simple. We have no idea how to control it. If you had a single actuator in the middle, you could revolutionize the postal service. You could have it self-sorting or something like this. If you could, I don't know what the applications would be, but it seems like a beautiful problem to sort of control falling paper, right? And we don't know how to do it with model-based stuff, but maybe you could do it with learning. Okay, so I think there's a cool story to be told there. Let me show you a couple other examples because I think you guys like the examples as much as you like the equations. So another sort of fun example is we worked on this hydrodynamic version of the cart pole. Okay, so here's a cart pole system. Okay, where now instead of having to fight against gravity, it has to fight against fluid dynamics. Okay, so it's sitting in a water tunnel. It's now a hydrofoil with its center of pressure behind its center of mass, and so basically, passively, it wants to weather vane around and go downhill, and you can pump up and swing it up and balance it against fluid dynamics. But it's horizontal in a water tunnel now. Okay, so this is roughly what it looks like. Don't want the pens to be selected. So that's supposed to be not dramatic, it's balancing, okay? We put a big inertial wheel in there to make it a little bit that's turned off, and it falls down in weather vanes around. Okay, so that's sort of like the simplest hydrodynamic control problem we could do. And then you could think about sort of cool things like what would happen if you were to shed a vortex at this cart pole and have it try to respond to the vortex, right? And that is actually a problem that I'm very interested in on robotic birds, because robotic birds respond to gusts of air in the wind surprisingly well, like beyond what you'd expect to be possible if they waited till they sensed them on the wing. So John built this experiment and did this. So now he's shooting vortices at the pendulum, and he's balancing it, whatever. But how did he do the control? He used these learning type approaches, but a mixture of the learning and the trajectory optimization that we've talked about to do sort of iterative learning control on the real physical experiment. Okay, so one of the cool things is he had this real-time particle image velocimetry, so he actually takes a laser sheet and gets the images off he gets to see the fluid in real time. People have done PIV for years. We just did a little extra work to make it so we could process 50 frames a second in real time and give it to a feedback controller. So if you see the fluid with particles and you throw a vortex, this is sort of what the vortex looks like. We did some basic image processing to pull out the vortex and make an estimator, so the pendulum knew when the vortex was coming. Some simple models of vortices, tracking them. Then the pole's here, the camera field of view is up here, and you get to basically tell the pole when it's coming and try to design a controller that could respond to that vortex. Okay, and the LQR controller with no adaptation had some pretty big response to it, okay? But then we tried to optimize it using the PIV feedback and an iterative learning control type approach. And you can see the with and without feedback approach. So this guy was trying to optimize, I'll play it again here. So there's two poles. One is the original system. The other one is the optimized system. It's trying to keep its pitch constant in this example. So the way it keeps its pitch constant is it actually comes and lets the vortex hit it right at the right spot so that the pitch is unaffected as it comes up. Sort of a beautiful result. It came and used the vortex to stabilize that motion. And it had a much better response than with the PIV feedback than without knowing the vortex was coming. Okay, and then the other one was trying to minimize the cart deviation. Oh, is that not going to play? That's too bad. That's the funny one too, because it's trying to just minimize the total X position, if you will, of the cart. And this one, when the vortex starts coming, it kind of goes like this. And it's like, I'll just let that go by. I'm not going to let that hit me. And it just slips to the side, and the vortex goes by, and it comes back. And that's the optimal, the approximately optimal solution. Okay, so this was the control design in this approach. It's almost the same as what we talked about before, but this time we used a little bit more of the LQR type approach in the middle. So we would do the same experiment a few times, fit a linear model to the time-varying response of the system, okay? Stabilize the trajectory with LQR, run the new controller, get a new linear model, wash, rinse, and repeat. Okay? So that's a sort of iterative LQR approach with a data-driven approach to learning the model. And that also converges nicely without using physics as the initial condition, but just using the data. And that's a more standard approach in iterative learning control world on the control side of the divide. One of the cool questions is, how much information do you need about the gust? How do birds know what they do? And it turns out that, long story short, if you only tell the hydrodynamic cart pole about the gust when it's almost right on top of it, we would delay, and show the cart pole the information about the vortex later and later. And at some point, there was a critical threshold where knowing the vortex was coming, it was irrelevant. Now, my best performance, knowing that the vortex was coming just before it hit me, was the same as if I didn't know it at all. And it took about 0.5 seconds of I had to know enough ahead of time that the vortex was coming in order to have a chance to respond actively to it. which again adds to the mystery of what the heck the birds are doing, because the birds seem to be able to wind hover in beautiful ways, getting knocked around by gusts, having almost no perturbations. And it just feels like if they have to wait until the gust hits their wings, it's too late, because it takes time for flow to evolve and for them to respond. So I don't know what they're doing. Maybe they're seeing the fluid coming towards them. Who knows? Okay, and then the one last example I want to show is a walking example, which goes back. It's my thesis work was actually doing all this learning control. It's kind of fun to look back when I did PowerPoint instead of HTML. Okay, so yeah, I was talking about Asimo back then, but I built a simple robot, partly because I was in a neuroscience lab and I didn't have much money, and I had just a little Shoreline mill, and that's the best I could do, really. But said, okay, let's do learning control, but let's try to build a robot to simplify the learning, okay? And so I told the story back then about passive walking, rimless wheels and compass gates, and cool robots that other people had built, right? And this was the robot that I actually got to build. You can see I couldn't even afford a ramp, right? So we had the CD rack that was from home because we didn't have many CDs even, and and then I had to cut out the rubber for something, and I couldn't get another rubber sheet, so I have a corner stick missing from my rubber. It's pretty sad, yeah. But built these little passive walkers that worked fairly well down a ramp, and then this is the actuated version of it. Okay, it's got now arms out here. Turns out that makes a big difference. If you're a passive walker and you're swinging your leg through, then you're dependent on your friction at the ground, but you'll have a tendency to twist. So this arm doesn't actually add any degrees of freedom. It's mechanically linked to the opposite leg. So it's just going like this, right? Just through that, looks like a roll cage, but that's just the connection here. And I put the batteries out there to make it have serious momentum, and basically it took out the yaw moment around the foot. Okay. This one has servos on board, so that when the servos are just holding their zero position, it acts like a passive walker, but it has the ability to add energy back in. And it's got a PC-104 in its belly, which is just hanging passively, and the mouth-looking thing is the USB Ethernet. Yeah. So a total of 9 degrees of freedom for actuators, always underactuated, right? And back then I said, okay, I've got this manipulator equations. I'm trying to write there's a state feedback controller. And I'm going to try to find the controller to stabilize the limit cycle solution on any slope, right? And so when the controller was just 0, it would walk down a ramp stably, just like that previous passive walker. It would pretty much walk forever. I put a couple little, basically I made the treadmill a little bowed, so it would have a tendency to go towards the middle, but it would basically walk forever on the treadmill. As I was writing my thesis, I just heard all day long. It was like, Edgar Allan Poe-like. Right? Okay, and then I wrote down a simple feedback controller, which just took the current velocity in one direction, and it had a linear combination of nonlinear basis functions on top of that. And I did policy gradient learning on it. Okay, so every time the robot took a step, I made a small change in the policy parameters, in the parameters W. I evaluated the change in the walking performance, and then I made a permanent change on W based on those results. So each of those tests is a noisy estimate of the policy gradient, and it was performing online stochastic gradient descent, right? So the big challenges in my mind were what were the right cost function for walking in this sort of online walking sense, and how did you get fast provable convergence despite the noisy gradient estimates? Okay, so you recognize return map analysis. I picked a surface of section. You can plot the return map, okay? So I said for the walking robot, we should do something like a return map based cost function, right? So this was the observation is the optimal return map would be the deadbeat controller, would be a flat line. So what I did for my cost function for walking was I penalized on each step. Wow, PowerPoint's slow. The one-step cost, every time the limit cycle came around, was just the Euclidean distance of the sampled return map from the optimal return map. Yeah? So I had some desired walking speed, and I'd look at that distance, and that was my one-step cost, additive cost formulation. Okay, and every time the left foot hit the ground, I'd evaluate that map, and then I did this gradient descent, this noisy gradient descent. And I'd added Gaussian random noise and did a couple tricks with remembering things from the past, and showed that it still performed stochastic gradient descent. And then I did extra work to do variance reduction with a value function. Okay, but the cool result was that I was trying to always emphasize fast online learning. Long story short, robot walked in about a minute and converged in 20 minutes every time I ran it to a good controller. And it went from a passive system, which had the fixed point was at the origin, right? So it would, when the controller was turned on, I would literally pull the robot by its head like this. It would run out of energy and stand still. I'd do it again. Hours after hours, I did this again. And then once the control worked, all the learning worked, then I would do this, and after a few minutes, it would start walking in place, and it would stabilize. And this was the return map that came out, right? Now, that is why you could ask, why isn't it going to be the flat? Why didn't it achieve a better controller than that? It could be a local optima. I don't know. I think the robot's not capable of perfect. It had actuator limits and things like that. But this was surprisingly stable over a large range of initial conditions. And in practice, I had a little robot that learned how to walk. So this was when I was paranoid about it falling, so I took the arms off and put pads on, okay? And I eventually wrote a little script to make it start. So it would pick itself up, run out of energy, stand still. After about a minute, it would walk in place. And then you start, I could just make it lean to walk around, and it would struggle a little bit, but it would adapt to stabilize that stable limit cycle. And then after a few minutes, it would be walking around. Never well, but, you could, oh, look at that. I beat Scott to that. I didn't realize that. I forgot about that. Scott's got his punch-a-lum videos that we always talk about. I guess we punched a long time ago. And I could tell you everything about the linoleum floor in E25 on the fourth floor by the time we were done. I could tell you every nook and cranny, because the robot would walk downhill into all the nooks and, up and out eventually. That was so even with all of this was walking towards the media lab, I'm not sure. Never made it. Even with all the tools we have today and all the things we've done to talk about passive walking and everything like that, I still think this was a pretty good solution for that robot. I mean, the modeling the dynamics of that rolling contact is pretty tough. To make it work right in practice, I had to add silicone to the feet, and it deformed in non-trivial ways, and I think the modeling the contact dynamics of that are pretty tough. The actuators were crappy at best. I really think modeling that would have been pretty tough. And this thing was the magic when these things work is when you can find a few parameters that meaningfully parameterize the control space you're interested in. Then even if your robot's complicated, if it's a fluid, if it's a walking robot, these tools can work really, really well. Right? So for me, the experimental surprises were that it was possible to perturb the policy parameters enough to estimate the performance gradient without visibly changing the walking gait. Right? So I was worried about how big beta would have to be, and it turned out it could be really small. Like, to the eye, you couldn't tell when it was learning or when it wasn't learning, but it would still always keep learning. Right? And then really simple approximations of the cost to go function made a big difference in the performance. Yeah, so that worked pretty well. Okay, so I want to leave you sort of with some of what I consider to be the big challenges going forward for all these things, and you know, for better or for worse, what I think maybe are the next problems that we should be working on, given everything I hope you've learned here, right? So for me, I think there's a standing challenge that, like I said, the pendulum swing up. I still think we're not doing as well with our massively advanced computational control design as a simple energy shaping controller, right? I think developing robust output feedback. Wow, what happened there? Even for simple models. Well, simple robots. But with rich sensor models, I think that's still a sort of an open challenge, right? So that means in general, that's going to mean, you know, capturing perception as a sensor, right? You know, how do I capture or bound or approximate the uncertainty of a perceptual system if it's going to be used in a feedback control loop? That's tough, right? Perception systems don't make Gaussian noise kind of errors. You know, our bird flying through the forest doesn't say like, oh, I thought the tree was 0.1 meters to the side, you know, but it's actually here. It's, sorry, I didn't see that tree, you know? And those are the kind of errors we have to deal with. And how do you do principled control design around that? I think, you know, and alongside this is robust online planning, I think, is super important. For me, I think we don't even know how to do some of the basic robust stuff when contact's involved. I've been happy with how much of the story in the class we could carry through to the contact case, but I think we don't know everything about contact yet and in collisions. I think, you know, how do we efficiently propagate uncertainty through there? And then do robust, stochastic, you name it. I think that's going to be, I think we've gotten pretty far in walking without doing this. I think for grasping manipulation, I think that's going to be really important. You know, I think we're ready maybe to try doing, let's say, principled rigorous control. For fluid systems and soft robots. I put them in the same place. But it's probably going to look a little different than what we've been talking about in class. Hopefully it'll use some of the ideas. It'll go beyond that. But you know, what are the principled ways to extract low-dimensional models of the system you're working on? Low-dimensional nonlinear models. There's great work on model reduction. Some work on model reduction for nonlinear systems. You know, I think that's going to be a really exciting area in the next couple of years. There's so many people building, including people in this room, building really cool soft robots. I think the control story hasn't really happened there yet. I really think there's a really important story to tell about exploiting structure more in all these algorithms? In the existing algorithms, to make them work for more complicated systems, more complicated environments, you name it. Like, so those of you playing with trajectory optimization, hopefully some of you think like, wow, that really worked for me. Some of you probably think, geez, that didn't work as well as I expected it to work on this. And I think as we find ways to write down the problem better, and I think understanding the physics and how it interplays with the numerics of the algorithm is going to be a part of that. That's going to be an important story going forward. And I really hope that an important part of the story is really more beautiful, simple experiments. Right? Falling paper. We were just talking in a meeting the other day, but we have a standing challenge or idea that we should just be able to build a paper airplane and throw it out the window here at MIT and have it make it all the way to Harvard, right? I know I can't go the other way, but I know the wind is going right down, right off the river. I think we have a fairly good chance of making it to Harvard. Coming back would be a lot harder. But things like this feel like they're just such a beautiful physical problem, but they also rely on planning under uncertainty and modeling the wind around buildings in the city, and they're fraught with a sort of numerical, computational complexity, but also with these very simple dynamics that underlie and that rule. So I don't know. That's my quick list of what I think you could do next, or hopefully, what the kind of problems that I'm excited about at least. I think I'm done. So hope you enjoyed that, and if you haven't seen it already, we've posted the project schedules and information and everything. It's on the website, and I'm looking forward to hearing from you guys next.